My name is David Brown, and I'm going to be covering MCUboot again, and kind of giving an overview update of multi-image support with it. Just kind of as an overview, the last few connects I've talked about MCUboot, giving an update of our current status and what's happening, and I'm going to do the same thing today, except we have new status. But to start with, what is MCUboot? The MCU part stands for microcontroller. So we're talking about devices that run at tens to hundreds of megahertz, have 100 to megabytes of ROM, this kind of small device. It's a bootloader. That's what the boot stands for. And its big thing is about establishing a root of trust. Its main job is to verify the images before either booting them or upgrading them. And this is done through digital signatures, that kind of thing. So, kind of basic overview of what's going on. We have memory, flash, on our chip. And these devices we'll get to in a minute, they are typically execute in place. And it's sliced up into pieces. These are like partitions, maybe on a hard drive, you might think of them. The bootloader sits at the beginning. There's this thing called slot 0, which is the application. There's a thing called slot 1, which is for updates. And this scratch area that is used to move data around. And then within the slot is a header, some code, a TLV, some status, and that kind of thing. That's a really fast overview. I'm going to go into more detail in a minute. So, MCUboot, this is to give an overview of where MCUboot fits into the picture. The project itself is an open source collaborative project. Molinaro is one of the contributors to it. And as I said, this is about establishing the root of trust, that the code that runs MCUboot, we basically require that be made immutable somehow so that we can trust that that code is always there. But the devices need to be updated, and what this does is it makes sure that what's updated, what's in Flash is valid before running it. So where are we at right now? We support what's called execute in place. I'll get to that in just a minute. So a majority of these MCUs run code directly out of Flash. The Flash is usually on the die with the rest of the SoC. And the code is, that Flash is memory mapped into the processor's address space, and it's executed directly there. MCUboot partitions the Flash into two slots, which I call slot 0 and slot 1 for lack of more exciting names. And then there's a scratch area, which is used. In order to update, you have to swap the images, and in order to do that robustly, you need a place that you can always store something when you're erasing Flash. So this scratch area is used for that. MCUboot can validate, currently we support RSA and ECDSA signatures, and it has the capability of detecting that slot 1 is newer than what's in slot 0, determining that it's valid, either swapping or overwriting the two images based on how it's compiled and configured. All right, I keep alluding to this. What is execute in place? So the idea here is, in a typical PC, there's a boot ROM, and code doesn't usually run out of the Flash. It's copied into RAM and executed out of RAM. It may be loaded then off of a hard disk or SSD or other Flash devices. For these smaller devices, the small amount of typically NOR Flash is mapped directly into the address space of the processor, and it just runs it. So what this means is, in order to run code in slot 0, you have to link it at, in this example, address 8000 hex. If you put it somewhere else, it won't work because it would try at some point referencing something at the address it was linked at. The upgrade is still linked at address 8000, even though it's put at a different address, in this case 42 and some zeros. So in order to upgrade, we have to move the code from slot 1 into slot 0. Or if you configure it as such, we actually swap them so that if something goes wrong, we can revert that and go back to what was there before. So for non-execute in place, and this is starting to show up in some devices, the code is copied to RAM before it's run. So although it lives at 8,000 hex in the flash device, the bootloader will copy it into RAM, say at 2 and a lot of zeros. The code is linked at that address. There's some neat advantages to this. You don't have to move things around in flash because it's not run directly. You can just load either slot into the RAM and you can run it. In fact, in the non-execute in place, the diagram's a little misleading. There's no need for a scratch section. There is just, it does need a place to store the state of what's happening. So that's not quite true. The diagram, when you execute non-execute in place, the processor does have to start somewhere. And this is typically done with either a small amount of ROM that is actually in the flash, or there's a mechanism where the processor can run out of flash. It's common for, say, a QSPI flash, although it's slow, to memory map that code so that it can boot and run the code. And then the first thing it does, this what I call BL0 here, is copy the bootloader into RAM so that it can run quickly. And then the rest of it is like the rest of the diagram. The code will be moved down a little bit, and everything runs as we said. So this is the kind of more realistic view of what this execute in place, non-execute in place is. So if you notice the title of the talk, it was about multi-image. I wanted to cover this non-execute in place for really practical reasons because the V8M development board that we have is this way. And so we have to consider what to do and how to support this. But what's really going on is this idea of multi-image. And you may notice it's a lot more complicated. So instead of slot 0, slot 1, and scratch, we now have slot 0S, slot 0NS, slot 1S, slot 1NS, and then our scratch area. Each of these having the header, the trailer, the TLV, and all that stuff. So the idea here is that we want to be able, we need more than one image that can be updated independently if needed. And these images run in different kinds of contexts. And what I mean by contexts, a really simple example is multiple CPUs. We have, this is a very rough diagram of it's the PSOC 6 device. We have two CPUs. They both share the same peripheral space, memory, flash, and there's an MPU in there that can be configured. But these processors have different roles, and the MPU is configured so that they have different permissions. Generally, the non-secure processor, oh, and there's a typo, there should be an NS on the non-secure one in parents, to make it less misleading. The non-secure side generally won't have access to the data of the secure side. And it's important to know this is not very much like SMP. Typically, very little of the memory will be shared. It's usually a small amount with maybe a mailbox or something for communication, but we don't want access to be going back and forth between them. So the other place that we have the need for two images is a trusted execution environment, V8M being what we're currently working on, where we still have a secure and a non-secure, but they are contexts within a single CPU. So you can kind of think of it as two CPUs, a secure one and a non-secure, but it's virtual, whether they're done on one piece of hardware. And again, only the secure side can configure the MPU. Most of the memory is not shared. The code lives in flash in this case, or in SRAM. And the protection is set up so the secure one can only execute that secure slot, and the non-secure one can only execute the non-secure slot. So how does this affect MCUboot? This little yellow thing on the left that I've put on each of these slots kind of breaks down what's metadata goes with the slot so that the bootloader knows what to do with it. And currently we have this little header at the beginning, which for the most part is a magic number, a version, and a length. Following the image is another little block of data that we call the TLV, which is a poor choice of names, which consists of a magic, a length, and then a sequence of tag length value items, just kind of a common data storage. And a typical example of this might be we have a SHA-256, we have a key hash. So this SHA-256 describes the hash of the header and the code that come before it. And then the key hash and the RSA signatures, the other key hash, the signatures, authenticate this with a public key that will be stored in MCUboot itself. And the idea is we can then verify that we know what image is running. So when we have multiple images, we end up with multiple manifests. So slot 0 secure has a header, code, TLV manifest, pad, update state. Slot 1 secure has header, code, TLV, pad, update state. Then we have slot 0, which non-secure. I think I should have rotated that. The slot 0 is on the left, slot 1 is on the right. But each one of them has its own manifest that describes the contents and has a key for it. And that's okay. The problem is, how do we know what to update? If you have an ABI change between your trusted and your non-trusted side, if you just update one of those without the other, it probably won't even boot, or weird things will happen. The system will be in a confused state. So we need to update both of them together, maybe. Other times we need to update just the application, and the ABI didn't change. There's no point in updating that secure code. So, I mean, what happens is, and it gets more complicated also, if you have to revert one of the images, well, do you revert the other one? And what are the requirements behind that? It turns out that really we just need all of those configurations, and it needs to be something that's specified. So if you think of this, we add some more tags. Simple way to think of this. We'll put in there, in addition to the SHA, we'll say, oh, we depend on a secure side that's less than this version and greater than this version. And the rest of it's the same. There's a signature. This way, the software can look at this and decide, if I update this one, the version of that won't be valid, so I need to wait until there's a newer version of the other one available. Or I need to do a revert, the dependency state, the other one needs to be reverted, or I can just revert one of the images. So the problem here, actually I'll get to the problem in a second. There's actually a proposal discussing this on the GitHub. It's a kind of an RFC with some ideas on how to do this, where we just add some additional information to the manifest and use that to do the updates. Another way to do it is to detach the manifest entirely from the images. So instead of this thing being appended to each image, we have this manifest thing that sits by itself, that's got the hashes of the two of the images, all the dependencies about both of them, the signatures. Well, that's kind of the problem here, is we don't have a way to encode the signatures of more than one thing. And we also have a deeper problem in that all this stuff in the manifest that we've added isn't protected. The signature is over the image, and there's nothing to stop an attacker from changing the dependency information, maybe require an old version of the secure side and a new version of the non-secure, which that combination results in an exploitable bug because it overflows some buffer that it couldn't have existed if the versions lined up correctly. The other thing is, where do we put the signature for the other slot in this? There's kind of two solutions to this. The first being we don't do this. We have separate manifests for everything. But the thing that I was proposing is to change the way that the signatures work. So currently we have a signature of the image. So to change this, we have the manifest itself, some beginning part of it with the hashes of the images and the dependency information. And then we sign that. So the manifest is self-signed and contains a hash of what images it describes. And this allows us to protect anything we want. If we add more data to the manifest later, it'll still be covered by the signature. So this is good, but it's complicated dealing with the two images and the single manifest. You start to get into questions of where do we put it? When does it get updated? What happens when both images need to be updated? What happens when one? Is there always a new manifest? But this is kind of the solution that is being talked about. And don't know if you know about this project called Suit. It was originally called FUD, for firmware update, and several people on the mailing list reported that if it was called that, they would be unable to use it. So they ended up changing the name to the Software Update for IoT, the Suit project. And this is a project to basically describe how this manifest should be encoded. There's a lot of documents with threat models, architecture, that kind of thing. But for the most part, it's about the manifest that MCUboot currently has its own approach, and so does Suit. So the idea is everything they decided is going to be encoded in CBOR, which CBOR is kind of like the tag length value, except some of the tags can be nested structures, so it defines hierarchical data. Think of it as a binary JSON encoding or something like message pack, but doesn't require as much code to parse. It was intended to be very simple to process. So the Suit manifest has a bunch of these things in it. And by the way, this is a working draft, and everything is subject to change and likely will be completely different when the next draft comes out. So this is why we're not implementing any of this yet. The current manifest has some stuff in it about nonces and sequences, conditions, directives, resources, which are slightly more complicated ways of saying the same things we just talked about in the other manifest. There's hashes of the images, and there's version dependency. And then there's all kinds of complicated stuff in there that we wouldn't really want in a real simple bootloader like we have. Let's see what this does. Okay, that will work. So what are we going to do? Actually, let's go back here. I missed the left part of the slide. In addition to this, so there's no signature in the Suit manifest. It's just data. There's another standard called COEs or COSA, depending on who you ask. It gets pronounced differently, which is a way of having blocks of CBOR data that are protected by signatures, possible encryption, and some other things. It's a pretty complicated spec, and it allows a lot of flexibility as far as you can have multiple signatures. You can add signatures of parts of the data later. And again, it's pretty complicated for code that lives in a bootloader that we'd like to be on the order of 16K. And fortunately, it's possible to say we support a subset of this, that we allow single signature or multi-signature images, just signed data, and that's it. And what it is it's some headers, some unprotected headers, payload, which would be the Suit manifest, and then the signatures. So what are we going to do? Here's the big question. What are the plans of MCUboot? As far as Suit goes, we're going to wait. The project is a working group. It's an IETF. It's a standards body. To say it moves slowly is kind of an understatement. We're working on various drafts, trying to get, you have a large number of participants that have pretty different requirements for what they want, and it takes some time to come up with something that meets all of those needs. There's not much point in implementing support for this because the next draft is going to be very different, and it's the encoding that's changing, and that's what most of the code is about. As far as non-XIP, actually this may not even be true anymore. When I made the slide, the goal was, yeah, we're going to do the non-XIP support because of this development board that we have. Whether we continue to support that or not is kind of up in the air. But this kind of mode is needed for some targets that do execute directly from, that execute from RAM and have to use MCUboot as more of a bootloader than a flash-based bootloader. And multiple images, yeah, we do need this. We have multiple targets from the V8M targets and the board, the PSOC 6, for example, I talked about with multiple CPUs that run out of the same flash. So about how to do it, I discussed two different approaches. The idea of multiple manifests, that's where we're going to start. So this is different than what Suit will end up with, maybe. But the idea is that we put extra data in each header to describe the dependencies, fix the signature problem so that it's verified, but otherwise we try to not make more changes to the bootloader than we need to. And as far as detached manifests, I think the big question there is to figure out, do we even need it? It's a big change from how things work now. It probably won't even be mandated by Suit, so I think we'll kind of just have to see. And that is indeed it. So that's all I've got today. I guess if there's any questions, now's a good time. And there should be microphones, if there's questions.
So how do we build a final image to flash with these multiple images for different CPUs inside?
Are you talking from a tooling point of view? I don't know. We don't really have a good solution to this yet. The way we're doing it right now is we have this big shell script.
Okay, and is it right?
Does it. Along with there's a Python script part of MCUboot that assigns and assembles the bootloader and the single image together. It seems reasonable to extend that to allow multiple images. Once you start needing to do over-the-air updates and stuff, more tooling will need to be created for that.
Yeah, and is it true that MCUboot itself now requires minute tool to be built?
No.
No. So in Zephyr, like workflow context, how would we build this final image?
Right. So right now, the easiest way to do this is in the MCUboot tree under samples, Zephyr, there is a make file, and it has a bunch of targets for all these different configurations we test. And if you just type make and one of those targets, it will build MCUboot using Zephyr with CMake in its system. It will build a Hello World application using Zephyr, and it will assemble those into an image that can be put into Flash.
Multiple images support will be initially done like that, and then
likely. I mean, honestly, I don't know that we've figured that out yet. We'll have to come up with some kind of solution, obviously. It probably won't end up being strictly tied to MCUboot because it's kind of a larger feature than just the bootloader. For example, the trusted firmware image, right now, most of the work is done in its build system. Where we actually want that is a different question.
Okay, thank you.
So if you come back to the slide where you have the multi-image support for non-XIP.
Let's see how long it takes to get back there. This
yes,
one?
Yes, no, the next, this one. Yeah. Then we can see in this slide that in fact the MCUboot is recoupled in the RAM.
Right, so, yeah.
Is it something we can optimize? Because
In an ideal world, MCUboot would be masked into ROM that lived in unchangeable ROM in the device itself. There is a security weakness in this, in that we're pulling code from an external flash device. That's our root of trust. We're pulling that in before we can trust it. A lot of the MCUs that execute from external flash don't have anything else to boot, but if they do, that would be we would need to put MCUboot as that role of the initial root of trust in some kind of different RAM, in some kind of different ROM, in order to get that root of trust. If not, I think we're pretty close to out of time, so well, thank you for attending.